Okay, so we're going to start with the idea of a gas, and a gas is just a bunch of particles inside a container, and they are moving freely. In general, the distance between two particles, for instance, the distance between this and this particle, is going to be much greater than the size of the particle. So the particles are far apart from each other, and that's what we mean by far apart. They occasionally collide, but this is not often, and in general, they don't interact. Okay, so this is the idea of a gas. Gases are fluid, and they flow and exert pressure. This gas can move as a whole, it flows, and also exerts a pressure against the walls of this container. Gases are compressible. By that I mean that you can change the volume of the gas. Another phase of materials is the liquid phase, and the liquid phase is, you can think of it as the particles being closer together, as opposed to a gas where the particles are far apart from each other. In a liquid, they'll be closer together, so there'll be some structure to the liquid. Okay, so they are close together, and liquids are also fluid, they flow, and they also exert pressure against the walls. However, liquids are incompressible. That means it is very hard to change the volume of the liquid. You have to exert really strong forces to change the volume, as opposed to a gas where you can change the volume very easy. An important quantity that is going to come up a lot in thermodynamics is the volume, and the units of volumes in the international system is meters cubes, and 1 meter cubes is about 1,000 liters. Liters is another unit for volume. 1 liter is about 1,000 centimeter cubes, and 1 meter cubes is 10 to the 6 centimeter cubes. This 6 here sometimes is a source of confusion. So uh, the way you think about this is that each side here of this cube has 100 centimeters, and when you multiply 100 by 100 by 100, you get 10 to the 6. Density. Density is just the mass divided by the volume. Okay, that's an important quantity that we are going to use a lot in thermodynamics. The units for density are kilograms per meter cubed. And here we have a small question for you to try. You have a piece of glass that is broken into two pieces of different sizes. What happens to the density? How do they compare? Is it A, B, or C? Take a minute to answer the question. Well, the density is not going to change. The amount of mass per unit of volume is not going to change because the glass breaks. So the densities of the three objects are going to be the same. These are some densities, typical densities. Here, this is an important one, water, and water is 1,000 kilograms per meter cubes. Another important one is air. Air is 1.2 kilograms per meter cubes. And then you have another one. You have mercury here. You can see how heavy mercury is. And oil is less dense than water, so that's why oil floats in water. And seawater is a little denser than the actual water because it has the salt. So pressure, this is the quantity that we want to understand very well. And consider this container and it has a liquid. And if you open three little holes here, you're going to get water coming out. And the water coming out of this lower hole it's going to come out with a greater force than the water from this upper hole. Why is that? Well, that is because of the pressure. So a container that has a fluid in it, a liquid, the liquid in that container is going to exert forces over the wall. of this container. So there's going to be a force here on this wall and a force here and here and here, and everywhere there's going to be a force, right? So we're going to define the pressure. The pressure is going to be you're going to take this force and divide by the area. And that is the pressure. That is the definition of pressure. So the pressure is defined as the ratio of the force to the area in which the force is exerted. The units of pressure are newtons per meter squared, also defined as Pascal. 1 Pascal is 1 Newton per meter squared. One property of the pressure is that the pressure is the same in all the points of the fluid. For instance, the pressure it would be the same along this line here. Right here along this line, the pressure would be the same. So the force that is acting on this piston would be the same here. And the same for these three pistons here. They would have the same force because they are at the same level. So because of gravity, the pressure increases as you go up or down, but it's the same if you go sideways. What is the origin of pressure? Well, it has to do with two things. We have to do with gravity and also the collision of the particles with the walls of the container. Every time a particle collides with the container, like this one here, then there is a force here on the wall of the container, and that force produces the average of all the forces on this wall is what we call the pressure. So there are two contributions to pressure. One is the gravitational contribution. Gravity pulling down increases the pressure. And the other one is the thermal contribution. Uh, Although we haven't studied temperature and heat yet, we can think of a gas, these particles moving randomly. The hotter the gas, the faster the particles will move and the greater the pressure. So at sea level, the pressure is 101,300 Pascal. So that is the standard that we call this the standard atmosphere, 1 amp, and it has this value, which I'm having trouble pronouncing, is 101,300 Pascal or 101 kilopascal. This is easier to say. So, and this is what happened. This is a picture of a gas in a container, right? As you come down here, you can see that there are more particles and therefore the pressure is going to be greater here than up above here. So here is a, a nice question. If you hold out your arm, which has a surface area of 200 centimeter cubes, the atmospheric pressure on the top of your arms is 2000 newtons. 2000 newtons is about 3 times the weight of a person that weighs 160 pounds, right? So, yeah, about 450 pounds. So, why can we do that? Well, the reason that we can hold that much weight is because if this is your arm here, right? You have the weight of the air above you, but there's also the same pressure below because the pressure is the same all over. So these two contributions cancel each other and actually your arm is not holding any weight. All right, thank you very much.